In this video tutorial, we're going to look at the concept of humidity by looking at the concepts of saturation mixing ratio, relative humidity, and dew point temperature. Central to all of these concepts, and the thing that ties them all together, is the relationship between air temperature and air's capacity to hold water. Essentially, air's capacity to hold water goes up as the air temperature goes up and goes down as the air temperature goes down. That's what's going to tie all these concepts together and allow us to compute one thing to another. So the key resource that we're going to use here is Table 4.1, which shows us the relationship between temperature on the left-hand column and the saturation mixing ratio on the right hand. So what this is telling us is that at a given temperature, air's maximum capacity to hold water is displayed on the right. So, for example, if we look at air that is at 10 degrees Celsius or 50 degrees Fahrenheit, we're going to look in the left-hand column of this table, find the 10 degrees Celsius or 50 degree Fahrenheit row, and then look across to the right, and we see that at that temperature, the maximum amount of water that air can hold is 7 grams per kilogram. If the air was holding that much water at that temperature, we would say it was saturated, which is another way of saying that its relative humidity is 100%, right? If the air temperature increased to say 30 degrees Celsius or 86 degrees Fahrenheit, its capacity to hold water will also increase. So how much water would we need to saturate air at that temperature? Well, again, we look at the table on the left-hand column, we find 30 degrees Celsius or 86 degrees Fahrenheit, and then we look across to the right, and we see that at that temperature, air can hold at a maximum 26.5 grams per kilogram of water. That is the maximum amount of water that the air can hold at that temperature. And if the air was holding that much water at that temperature, we would say that its relative humidity was 100% or that it was saturated. Those things are equivalent. So let's look at a scenario. If the temperature in St. Paul, Minnesota is minus 10 degrees Celsius and the relative humidity is 100%, how much water is in the air? Well, we have two pieces of information that are important here. We have the temperature of the air and we have the relative humidity. Since we know that the relative humidity is already 100%, the air is saturated, the question is, what amount of water would saturate air at that temperature? So again, we refer to the table. We look for, on the left-hand column, minus 10 degrees Celsius, which is equivalent to 14 degrees Fahrenheit, and then we read across to the saturation mixing ratio column, and we find that at that temperature, 2 grams per kilogram of water in the air would saturate the air. So at 100% relative humidity, essentially that's 1 times that amount, which is what it is. But more intuitively, it just simply says that the air at that temperature is holding as much water as it possibly can, and that's what's told to it. That's what the table shows to us. So let's look at a warmer place. If the temperature in Phoenix, Arizona is 25 degrees Celsius and the relative humidity is 20%, how much water is in the air? Well, in this case, we know that we're not at saturation, we're at 20% relative humidity, so the air still has capacity to hold more water. But we still need to know what that capacity is for that temperature. So it's 25 degrees Celsius, so again we look at the table, and on the left-hand side we find 25 degrees Celsius, which is about 77 degrees Fahrenheit, and we see that at that temperature the air could hold up to 20 grams per kilogram of water, but it's not saturated, so it's not holding that much water. It's only holding 20% of that. So the way that we can figure that out is to take 20% of that potential. So we know that it can hold 20 grams per kilogram at that temperature. 20% or 0.2 times 20 grams is going to give us 4 grams per kilogram. So the actual amount of water in the air is 4 grams per kilogram, 4 grams of water per kilogram of dry air. So that's the amount of total water that's in the air. Now, what if the temperature in Phoenix dropped from 25 degrees Celsius to 20 degrees Celsius, but it contained the same amount of water? So we didn't change the amount of water in the air, we just dropped its temperature. What would happen to the relative humidity of that air? Well, because air's capacity to hold water is dependent on temperature, the relative humidity is going to change because the saturation mixing ratio is going to change. So again, we look at the table and we look in the left column, we find 20 degrees Celsius or around 68 degrees Fahrenheit, and we see that at that temperature, air can only hold 14 grams of water per kilogram of air. Okay. Now we know that it already has 4 grams because we computed that previously. So what we're going to do is we're going to take what the air is actually holding, that 4 grams, and then we're going to divide that by the potential 14 grams. So we take the amount of water that's in the air, right? That's the mixing ratio, which is the actual amount of water in the air, and we divide that by the amount of water the air could hold, which would be the saturation mixing ratio for the air at that temperature, at 20 degrees Celsius. So we divide what's in the air, the mixing ratio, 4 grams, by 14 grams, which is the potential, and we end up with 0.29, which we want to turn into a percentage, which turns out to be 29%, right? So interestingly, if you noticed already, there was more water in the air in Phoenix, 4 grams per kilogram, compared to St. Paul, yet the relative humidity is lower, right, in Phoenix compared to St. Paul. And that's because the capacity of the air in Phoenix is much higher. It's like a giant sponge compared to the little sponge in St. Paul. What if the temperature in St. Paul rose to 5 degrees Celsius with the same mixing ratio of 2 grams per kilogram? What would the relative humidity be? Well, if you increase the temperature, you're going to increase the capacity of the air to hold water, right? So at 5 degrees Celsius, right, now the air can hold up to 5 grams per kilogram of air, right? So I'm getting that from the table, right? And the question was, how much water did it have before? It had 2 grams per kilogram before. That's what we determined earlier. So we had the same process. We take the actual amount of water in the air, which is the mixing ratio, which we calculated earlier, and we divide that by the amount of water that the air could hold at that temperature, in this case 5 degrees Celsius. So we take the 2 grams that it's actually holding and we divide it by the 5 grams it could hold, and we're going to end up with 0.4, which we multiply by 100 to get 40%. And so thereby we can get the relative humidity by knowing the temperature and the mixing ratio, which is another way of saying the amount of water in the air.